lecture, we started with strength of material approach. And as far as concerned with the strength of material approach, we have seen the representative volume element. Okay. So while considering the representative volume element, the purpose to use the strength of material is to evaluation the four elastic modulus. Is it okay? As already now we are familiar with the thing that in order to identify the structural properties, in order to identify the stress, strain, displacement, deformations, etc., we need the these elastic constants. Is it okay? So during this macro mechanical analysis, we have seen that the kind of material based on the type of material, how many number of independent elastic constants are required. So now this is the micro mechanical approach. And micro mechanical approach inside which we require that properties based on this matrix and reinforcement. What is the percent of matrix? What is the percentage of reinforcement? Based on that matrix and reinforcement percentage, these properties we are identifying. Is it okay? So the purpose is to identify longitudinal Young's modulus, transverse Young's modulus, major Poisson's ratio, and in-plane shear modulus. Is it okay? The strength of material approach we are going to use now. See, so representative volume element. For that purpose, let us first of all see the figure here. Is it okay? So this is the particular part which we are taken into consideration, and out of which this small, this is the representative volume element. Is it okay? We take this as a representative volume element. So this total composite material, we are considering this as a total composite material plate. So for this composite material plate, the whatever the small parts which is shown here, these are the reinforcement. Is it okay? And remaining part, remaining body part which is present here in between these, this is considered to be the matrix. Is it okay? So alternate this matrix and reinforcement is present. If we take this small element for this study, this is the small element which we have taken to the study as shown here. Here it is shown that this is the taken for the study, and then this part becomes as a, which is shown here. This part becomes as a representing volume element, which is called as RVE, representing volume element. Now this representing volume element consists of what? This part is reinforcement, which whatever the central part is, round part is shown, that is the reinforcement, and remaining part which is around this is considered to be a, this particular round part which is around this, which is considered to be a matrix. Is it okay? So this is the total RVE, representing volume element, inside which this much part is the reinforcement, the remaining part is the matrix. For that, let us consider this as a H, as a height. Is it okay? This is considered H to be a height. Similarly, this particular portion which are considering the thickness, and this we are considering to be a length. Is it okay? So this is the, from this end to this end, this we are considering to be length. Then this length, this part to this here, we are considering this as a thickness, and here we are considering to be a height. Is it okay? So height, length, and thickness, that we have considered here. Then coming to this much part here, suppose this whatever the reinforcement part is shown here, in that reinforcement part, let us consider this part as a thickness of reinforcement element, and this particular part from this end to here, this as a thickness of, half thickness of matrix material. Remaining half thickness of matrix material is shown here. Is it okay? So half thickness of this particular region is of matrix, this particular region is of matrix, and this particular middle region is of reinforcement. Is it okay? So this total composite or representative volume element of the composite consists of matrix and reinforcement. Is it okay? Where this portion is matrix, this another portion is matrix, and in between that this portion is reinforcement. Is it okay? Here also at the top surface we can See here, this is the matrix, this particular region is matrix, and in between here only there is reinforcement. Is it okay? So the total thickness of the matrix, if it is Tm, out of which half is present on this side, half is present on this side. So that's why this is considered to be Tm divided by 2. The meaning Tm divided by 2 is half of matrix length. And here Tr is nothing but a thickness of reinforcement. Is it okay? So thickness of reinforcement and half thickness of matrix material. So that total will be considered to be thickness of composite material. Is it okay? So now let us come for some assumptions. So here we have considered, while using the strength of material approach, that this is a unidirectional lamina. Is it okay? Here unidirectional. This is only one direction. This end to this end, like this. This end to this end. This is only unidirectional lamina, which we consider as unidirectional lamina, and which consists of a representative volume element, and that consists of fiber surrounded by matrix. Is it okay? And then the fiber matrix and composites are assumed to be a same width, height h. Tf, Tm and Tc in these particular notations which are used here. Tf represents the thickness of fiber, Tm represents the thickness of matrix, Tc is used notation as a thickness of composite material. Is it okay? So the area of matrix which is given here, for that purpose the notations AF, area of fiber, area of matrix and area of composite material. Is it okay? Here these three equations A, B, C, these three equations are equation of area of fiber, area of matrix and area of composite material here. So the area of matrix, the area of composite, which are represented with reference to the TFH, TMH and TCH. So TFH, thickness of fiber into its height, thickness of matrix into its height, thickness of composite into its height. With these two dimensions, this area of fiber, areas of matrix and area of composite is calculated. Is it okay? Now, if suppose we are interested to identify the volume fraction, so already we are familiar with this concept of volume fraction. So volume fraction of fiber, for that purpose we consider Vf upon Vc. Vf upon Vc. So Vf is nothing but Af into with reference to this AF area, because in order to calculate the volume we always take area into length. Here length is same for all. Is it okay? If we consider this as a length, already we are used this as a length. Then for this length, the length of matrix is this much, length of fiber is also same this much, and length of composite is also same. So that's why length of composite material, length of matrix material, length of reinforcement material, all these lengths are same. If length are being same, then area into length, that will become the volume. So volume of fiber, for that purpose AF into LF, and volume of composite, for that purpose AC into LC. But both L are same, so L will get cancelled here. AF upon AC, that we will have to take into consideration here. So volume fraction of fiber, which is nothing but AF upon AC, as far as concerned with this area of fiber or area of composite, we are using the notation here T suffix F and T suffix C here. Is it okay? So thickness of fiber and thickness of composite, that we are taking into consideration, because area, for that purpose already we have used AF is equal to TF into H and AC is equal to TC into H. H will get cancelled here, we will get only TF upon TC. So volume fraction of fiber is nothing but thickness of fiber to the thickness of composite here. Is it okay? Similarly, if we take the volume fraction of the matrix, then that will be definitely the remaining part. That means 1 minus Vf is equal to Vm. Is it okay? So this matrix, for that purpose again, if we use the same formula, volume fraction of the matrix, which is again Am upon Ac, Tm upon Tc, which is nothing but 1 minus Vf. So Vm is equal to 1 minus Vf here. Is it okay? Now for this strength of material approach, what are the assumptions? Inside there, the first assumption is the bond between fiber and matrix is perfect. Elastic modulus, diameter and space between fiber are uniform. Fibers are continuous and parallel here. Is it okay? So once again, we should elaborate these all things here. This is the stress present inside the composite. Sigma C is the stress present inside the composite. Tf is the thickness of fiber. Tm is the thickness of matrix. Half portion of this matrix is on this side, half matrix of the portion on that side. That's why Tm upon 2, Tm upon 2. So total, this end to this end, this is the composite. So that's why Tc is here. This height is h here. So fiber and matrix follow Hooke's law. This is one assumption. Fiber possesses uniform strength and composite is free from wide. These are certain assumptions present here. Is it okay? Then let us first of all calculate the longitudinal Young's modulus. Is it okay? Because we have seen that we have to identify the different elastic constants, and within that elastic constant, longitudinal Young's modulus is one of the we can say it as the elastic modulus. Is it okay? So now if we consider that load is applied on this particular composite material, because suppose this is the direction on which the forces are applied. Is it okay? This is the direction in this direction we are considering the forces are present. Is it okay? So this is the direction in which this force is present. In this direction this force is present. So if total force acting on the composite is F suffix C, total force acting on the composite is equal to F suffix C, then that will be beared by both. That means that one of the load which comes on the fiber and some of the load which comes on the matrix. So the load coming on the composite material is nothing but load on fiber plus load on matrix here. Is it okay? So this Fc is nothing but F plus F M. Is it okay? So with these usual notations, what is Fc, what is Ff, and what is Fm, that you should understand here. Is it okay? Then Fc is nothing but, as usual notations, sigma c is the stress. So stress is equal to force upon area. So that's why force is equal to stress into area. So Fc, if it is the force acting on the composite material, then definitely it will be the stress on composite material into area of composite material, with the regular definition of stress and force. Then if F is the force acting on the fiber, then definitely that is the stress on the fiber into area of fiber. Then Fm, which is nothing but the stress acting on the matrix into area of matrix. Is it okay? So sigma C, sigma F, and sigma M represent stress acting on composite, fiber, and matrix respectively. And A suffix C, F, and M represents area of composite, fiber, and matrix respectively. Is it okay? So this is the sigma and A meaning. Then let us consider sigma C. As far as concerned with the relationship between stress and Young's modulus, what we can say, Young's modulus is stress upon strain. Okay. Our regular definition of stress is equal to of Young's modulus is equal to stress upon strain. Then stress is equal to Young's modulus into strain. Is it okay? So with this particular equation which is shown here, with this equation we can consider stress acting on composite material is equal to this Young's modulus into strain acting on composite material. Is it okay? So that is the relation. Now E1. See here the concept of linear and lateral will start, because in case of this unidirectional lamina, always Young's modulus in linear direction is different and in lateral direction is different here. Is it okay? So stress acting on composite material is equal to Young's modulus into strain acting on composite material. Definitely, stress acting on fiber is equal to Young's modulus acting on the fiber into strain acting on the fiber. Is it okay? And same thing will be applicable for matrix material also. So stress acting on matrix is nothing but Young's modulus of matrix into strain on matrix. Is it okay? So with usual notations, strain epsilon is the notation used for strain. CFM is used for the composite, fiber and matrix respectively. Is it okay? Then E1 Fm, that represents the Young's modulus or elastic modulus for composite, fiber and matrix. Is it okay? Here the notation 1 is used, not EC is used, because this EC is different for this linear direction and lateral direction. 1 represents linear direction and then lateral direction will also come. Is it okay? Then by substituting all these equations in this stress equation, is it okay? So substituting this equation 3.31 in equation 3.29 indirectly. So FC is sigma C into AC. So here is sigma C into AC, sigma F into AF, sigma M into AM, and alternative sigma C is nothing but E1 epsilon C. So substituting here En epsilon C AC is equal to EF epsilon F AF is equal to plus EM epsilon M AM. Is it okay? So this particular is the force acting on the composite material. This is the force acting on the fiber material, and this is the force acting on matrix material. So force acting on composite material is addition of force acting on fiber material plus force acting on matrix material. Is it okay? So the forces like this acting on composite, fiber and matrix, these three can be represented in that way. Is it okay? Then as far as concerned with this particular equations, so E1 epsilon C AC is equal to EF epsilon F AF plus EM epsilon M AM. So for that, the strain in the composite, fiber and matrix are equal. So epsilon C is equal to epsilon F is equal to epsilon M. The strain acting on this composite, fiber and matrix, if considered to be equal, to be a same, then from this equation epsilon E1 EF EM, for that we may consider that this particular AC is, which is represented at this left side, will be now transferred to the right side, which will go in the denominator part. Is it okay? So E1 so as strain is same in all time, because strain is change in length to the original length. If length is going to change, then fiber will also expand with same dimension, matrix will also expand with same dimension, and composite will also have same dimension. Is it okay? So change in length will be same for all and original length is also same for all. That's why strain for all will be equal. That quantity will get cancelled here, and then the Young's modulus in longitudinal direction, or Young's modulus in this particular direction of the force application, which is considered to be E1, is nothing but EF AF of AC plus EM AM upon AC. But already we have seen that AF upon AC is what and AM upon AC is what. AF upon AC is nothing but VF, and AM upon AC is nothing but VM. Is it okay? So the Young's modulus acting on the composite material in longitudinal direction is nothing but EFVF plus EMVM. Is it okay? So try to take into consideration this particular concept. So whenever we are going to calculate the Young's modulus, then that Young's modulus is nothing but EFVF plus EMVM. So E1 is equal to EFVF plus EMVM here. Is it okay? Then the ratio of load taken by the fiber to the load taken by the composite is a measure of the load shared by fibers. So from this equation 3.30 and equation 3.31, which is present here 3.30 and 3.31 here. So this equation 3.34 already now with us, that is how to calculate the Young's modulus in longitudinal direction, that we have known. So that is proved here. Is it okay? Now we are going for this next equation, that is from equation 3.30 and 3.31. So what is 3.30? 3.30 is this ABC, and this 3.31 is sigma C sigma F sigma M. So here the force acting on fiber to the force acting on composite material is nothing but this EF VF EF AF upon E1 AM. This is nothing but the volume fraction of fiber material. Is it okay? So that's why this particular equation is calculated here. Is it okay? So from this, the ratio of load carried by the fiber to the taken by composite is plotted here. So if we check this particular figure, we will come to know that as volume fraction starts to increase, initially when volume fraction is 20%, then 40%, 60%, 80%, as volume fraction starts to increase from 20 to 80%, then definitely its effect on fiber to matrix modulus from EF to EM, that is changing here. Is it okay? So here we can consider with this 0.2 to 1 fiber to composite load FF to FC, how this is going to change here, and with reference to that, this fiber to matrix modulus EF to EM ratio, how it is changing here. Is it okay? So based on that, this is one simple example. Find the longitudinal elastic modulus of unidirectional glass fiber lamina with 70% fiber volume fraction. Use the properties of glass and epoxy from table given here. So with reference to that table, we have Young's modulus for the fiber, that is carbon fiber, is 85 gigapascal, because in this example it is mentioned that glass epoxy. So sorry, here glass. So Young's modulus of glass, which is given here, it has 85 gigapascal. Young's modulus of epoxy, which is given here, it has 3.4 gigapascal. Is it okay? Then with this, the longitudinal elastic modulus of unidirectional lamina, which is E1 is equal to EMVM plus EF VF here. So this is EF VF plus this is EM VM. As here it is mentioned that 70% fiber volume fraction, that's why 70%, which is converted as 0.7 here. So 85 into 0.7 plus 3.4, this is the percentage of the matrix, this is the percentage of the fiber, this is Young's modulus of fiber, this is Young's modulus of matrix. Is it okay? So E1 is equal to EF VF plus EM VM. So all these values are substituted, and then we have identified the Young's modulus in longitudinal direction. So the longitudinal elastic modulus of unidirectional lamina we got as a 60.52 here. Is it okay? So like this, additionally, we have identified this force acting on fiber, force acting to composite, that ratio For that purpose, this 85 is the Young's modulus of fiber. This is Young's modulus of composite, and this is the percentage of volume fraction of fiber. So, with this example, with this particular equation, we have identified the ratio of force acting on fiber, force of acting on composite, and it means that 98.31% of the load is carried by fiber only, and only 1.69% that much amount of force is carried by matrix material. Is it okay? So see how fiber takes load in case of composite material. Is it okay? So additional to that, one more elastic modulus we will share here with the same figure. Now the force acting is in this direction. Is it okay? So see, check here. In previous example, we have considered a load in this direction. Is it okay? This was the direction of load in previous figure, but now we are considering the load in another surface. Is it okay? This is the lateral direction. If this we consider as longitudinal, definitely these two are the lateral directions. And suppose force is now acting on the lateral direction, then what is going to happen here? That we will have to see. Is it okay? So delta is the deformation happening in the composite material. So if delta C is the deformation of the composite material, then delta F and delta M. So delta F is the deformation in fiber plus delta M is the deformation of matrix material. Is it okay? So this delta C is equal to delta F plus delta M. So deformation of composite material is equal to deformation of fiber plus deformation of matrix here. Is it okay? Because what happened in this direction, whenever we are considering this particular direction, so this is the longitudinal direction, expansion happened in this longitudinal direction will be same for fiber, matrix and composite. But if we consider the expansion happening in this direction, which is shown here, that will be expansion of matrix plus expansion of reinforcement. So expansion of composite material will be the addition of expansion of matrix and expansion of reinforcement material. Is it okay? So here we have used this particular formula, simple formula, delta C is equal to delta F plus delta M here. Is it okay? So delta C like this is given as with usual net notations, the deformation or change in length is nothing but the strain on in general, strain is nothing but change in length upon original length. So change in length is delta C and original length is TC. Is it okay? So change in length to the original length is nothing but this strain here. Change in fiber length to the original fiber length is delta F upon TF, which is the strain here. Is it okay? Similarly, change in matrix or change in length in the matrix to the original length of the matrix is nothing but strain in the matrix here. Is it okay? So thickness of composite fiber and matrix that is given by TCFM. Normal transfer strain in composite fiber and matrix is given by this epsilon ECFM. So the strain in composite material is given by this sigma C upon E2. Is it okay? Earlier we have used the notation E1, but now we are using the notation E2. E1 was representative of longitudinal this modulus, Young's modulus, but E2 represents the lateral Young's modulus. Is it okay? So E2 is the notation used for identifying the Young's modulus in the lateral direction. Is it okay? That we can see here how this E2 is used. Is it okay? So strain on composite material is nothing but this stress on composite material upon Young's modulus in lateral direction, because with usual notation we say that Young's modulus is stress upon strain. So E2 is equal to sigma C upon epsilon C, and EF is nothing but sigma F upon EF, that is used here. Epsilon C, epsilon F, epsilon M, that is the strain on composite material, strain inside the fiber, strain inside the matrix. Then substituting all these equations, this 3.39 in equation 3.37 and 36. This is 37. Here it is, and 3.36 here. Stress is same. Here we have considered stress on composite material is stress on fiber material is stress on matrix material. If stress is same and if deformation is given by this way, then substituting these values in these equations, we will get 1 upon E2 is equal to 1 upon EF TF upon TC plus 1 upon EM TM upon TC, which represents that 1 upon E2 is equal to volume fraction of fiber, because we know this particular ratio TF upon TC is nothing but volume fraction of the fiber, and this ratio TM upon TC is the volume fraction of matrix material. So substituting them, 1 upon E2 is equal to VF upon EF plus VM upon EM. This is the simple, we can say it as the derivation to identify the Young's modulus in lateral direction. Now the previous example same is repeated here, but only here it is asked to identify the shear Young's modulus in lateral direction. Is it okay? So substituting these values, we got Young's modulus in lateral direction as a 10.37. Previous in E1 direction it was 60 point something, but now it is 10.37. So how we can see the differentiation between these two? That is, in longitudinal direction it is near about 60, but in lateral direction here it is about 10.37. So in longitudinal direction it is 6 times more than lateral direction. Is it okay? Young's modulus difference in longitudinal and lateral direction, that is the representation that how the material properties in different directions are different. So that's why we can't say this as a we can an isotropic. We can't say this as isotropic material, and this isotropy changes in orthotropy in this kind of materials. Is it okay? So this Young's modulus, same figure which was previously drawn like this, here it is also plotted in order to find this. Is it okay? So with this this part of strength of material approach to identify the Young's modulus in lateral and longitudinal direction, that much part is over here. So anybody, any doubts with this?